Good morning, everyone. We're looking at a ladder question today, which is another example of a typical exam question that you may get on your exams. So I've framed up a question here. Got a diagram on the board over there. We're talking about a 3-meter long uniform ladder. What does uniform mean? It means that the weight can be considered to act through the middle of the ladder. The ladder's mass is 24 kilos. The top of the ladder rests on a smooth wall. What does smooth mean in physics? It means that we can ignore friction. The base of the ladder is 1 meter away from the wall on rough ground. Put all of that on the diagram. What does rough mean in physics? It means that we have to take friction into account. The first part of this question is, what's the reaction force of the wall on top of the ladder? Now the wall can do one of two things to the ladder. It can provide a perpendicular reaction force away from the wall, and I'm just going to label that RW. And if the wall was not smooth, there'd also be a frictional force stopping the ladder from sliding down the wall in the opposite direction to which the ladder would normally move. Okay, but I'm going to get rid of that because we are told that the wall is smooth. No frictional force between the top of the ladder and the wall. Right, and I'm also going to address part B is asking us what's the total reaction force of the ground on the base of the ladder. Alright, well clearly we can break up the total reaction force into two components. The first is going to be the component of a vertical component, let's just call that RV, and a horizontal component, let's just call that RH. Alright, now the vertical component is just the reaction force that the ground exerts on the base of the ladder. RH is equal to the frictional force that the ground provides to stop the ladder from sliding that way. Remember, that's what the ladder kind of wants to do. It wants to slide in this direction, which is when accidents happen. If the ladder is unstable. So there's a frictional force, which we call it RH at the base of the ladder. There's no frictional force at the top of the ladder because it's a smooth wall. The ground is rough. Okay, so the first thing I'm going to do is to, again, just put in the weight of the ladder, which is 24 times 9.8 newtons. Alright, now the first thing I'm going to do is to figure out RW. I'll label my points here, like I've always done. That's point A, call this point B, and I'm going to call this point C. Okay, now, we don't know very much about RV and RH at this point. So it makes sense to take our turning point, which we could also call our fulcrum, or which we could also call our pivot. I'm just going to refer to this point as the turning point, as the point where we know the least amount of information about, which is this point. Now, if we take A as our turning point, we can forget about RV and RH for the moment. Alright, so to find RW, I forgot one thing. No, in fact, let's do this. To find RW, let's take our moments about point A. Alright, now we are going to need one bit of information. Guys, we know that this distance is 1 meter, we know this distance is 3 meters. I do need this distance over here, you'll see why in a moment. And if we just use Pythagoras, because we've got a right angle triangle here, we can see that we've got 3 squared, subtract 1 squared. You can figure that out later. And I've already done this with the calculation. It comes out to 2.83 of a meter. Alright, now if we take A as our turning point, there's a couple of forces here that are actually in equilibrium, causing the ladder to be in equilibrium. First is the weight of the ladder, which is tending the ladder about point A to rotate in an anti-clockwise direction. Then there's the reaction of the wall on the top of the ladder, which is tending the ladder to rotate in a clockwise direction. And that's our unknown, so let's keep the clockwise moment on the left-hand side of our equation. Okay, so to find the RW, let's take moments about point A, and the sum of the clockwise moments must equal the sum of the anti-clockwise moments. moments. Let's work that through. What's the clockwise moment equal to? Well, it's going to be equal to RW times the perpendicular distance from the line of action of the force to the axis of rotation. Well, here's our axis of rotation. That's the distance. That's the perpendicular distance that we're moving through. We've worked it out to be 2.8 square meter. 2.83 meter. And what is our anti-clockwise moment going to be equal to? Well, it's going to be equal to the weight of the ladder. It's 24 times 9.8 multiplied by the perpendicular distance from the force to the axis of rotation, which is half a meter. So we've got 24 times 9.8 times 0.5. Okay, RW then works out to be, I worked it out, RW works out to be 41.58 newtons. And I'm going to round that to 41.6 newtons, and I'm going to underline that. And let's put direction in there as well. Perp to wall. Okay, now that's a good answer for part A. Alright? Pause the video if you need to actually think about this part of the question. Oh, no, not you. I'll keep going. I'll talk to the audience. Part B, the total reaction force of the ground on the base of the ladder. Well, look at this. People just look at this diagram. We now know a lot about the components that make up the total reaction force of the ground on the base of the ladder. Look at it. RV is an up force. There's only one other down force. There's only one down force acting in this diagram. That's the weight of the ladder. So therefore, RV must be equal to mg. Okay, let's put that on the board. Okay, I'm just going to say to find, this is part B, to find Rg. Okay, that's the total reaction force of the ground on the base of the ladder. We can say that Rv must be equal to mg, which is equal to 24 times 9.8, which I have worked out to be 235.2. 235.2 newtons. I'm not going to underline that because that's not my final answer. Alright, now what's RH? RH, which is the horizontal component force of total reaction force of the ground on the base of the ladder. Wow, I speak fast. That's going to be equal to RW, one force to the left equals one force to the right, which is going to be equal to 41.58. Notice I didn't round off, I'm keeping this nice and accurate for the moment. Didn't round off to 41.6, which was our final answer for part A. All good? Now what we now have to do is to actually work this through. I'm going to do this, I'm going to draw a line straight down here. I'm going to draw a diagram and think what this looks like. Now this looks like, as a vector diagram, there's RH, that's RV. I'm going to add these two vectors vectorially. This is not to scale, and this becomes our total reaction force of the ground on the base of the ladder. This is not to scale, by the way, okay? And let's work that through. The reason I've done it this way is because when we find our angle, we can actually reference that directly from the ground. Alright? So, what's Rg going to be equal to? Well, we know that Rg squared, just using Pythagoras, is going to be equal to opposite. Sorry, one mistake. Okay, the total reaction force squared is going to be equal to Rv squared plus RH squared. Just working that through. Therefore, Rg is going to be equal to the square root of, now what's Rv? Rv is 235.2 squared plus 41.58 all squared. I've kept everything nice and accurate for now, and Rg works out to be 238.8. Newton's just using Pythagoras. I'm not going to round off just yet. Okay, to find theta. So I've got the magnitude of the total reaction force. What's the angle? What's the direction that we're looking at? So to find theta, I can say that tan theta. Why tan? Because we have got a number that represents the opposite side of this right angle triangle and the adjacent side. So tan theta is going to be equal to RV on RH, and so therefore theta is going to be equal to inverse tan of RV on RH, which is what's RV is 235.2 divided by 41.58, and I've worked it through. Theta comes out to 79.9 degrees. Now we're all done. Just make a final answer. Final answer is going to be RG is 239 newtons. I'm going to round to three significant figures. 79.9 degrees to the ground. And I'm going to underline that as I always do. Alright, so nice picture, lots of information. I've solved the question. I've shown all my steps. I've given the final answer to three significant figures because that was consistent with the data that I was given. I've given a direction because we're talking about force, which is a vector, and I've underlined my final answer. There is absolutely no doubt in an examiner's mind as to what my final answer is. It's going to be this one here that's underlined. Thank you. So here's a question that's, it's a qualitative question that comes up in tests or exams. Why do people fall off ladders? Well, I'll climb this ladder in a moment. But if you remember from the question that we worked through on the board, there are two horizontal forces that are acting. The first is the horizontal force that the wall applies to the top of the ladder, and the second is the horizontal component of the reaction force of the ground on the base of the ladder. And this is actually also equal to the frictional force that the ground applies. So RV on the calculation is equal to the force of friction. And so long as these two forces are balanced, there's no problem. In other words, so long as the reaction force on the wall, which is the force to the right, is equal to the force of friction that the ground can provide, so long as those two forces are balanced, there's no problem. The ladder's not going to slip. The problem is that as we climb higher up ladders, this force gets bigger. Okay, the reaction of the wall on the top of the ladder gets bigger. And I'm going to prove that to you by asking Jonathan to be the wall. Now, Jonathan, you can stand there, okay, and if you can support that. Now remember the force that the wall supplies to the top of the ladder is a horizontal force, so Jonathan's arms now represent the top of the ladder, if you like. I'm just going to tilt this a bit more. And as I climb the ladder, I'm on the first rung now. Okay. Now, Jonathan, as I climb up the ladder, you should find that you're going to have to push harder with your arms. Is that right?
Yeah.
Okay, I'm going to go. Can I go one step higher?
You sure can.
Okay. How does that feel?
Yeah, that's a lot harder.
A lot harder, okay. And guys, that's why ladders slip. Because you can see that as I was climbing higher, the reaction force provided by the top of the wall to the top of the ladder was so big. The frictional force on the ground was like this. So long as those two are equal, there's no problem. But at some point when you climb up a ladder, unless the ladder is very secure, the reaction force that the wall supplies on the top of the ladder is going to become bigger than the force of friction that the ground can provide. And when that happens, the ladder slips and you fall. So a very good lesson is that in order to not be a statistic, because I believe that one of the biggest sources of trauma in emergency wards are men over the age of 50 falling off ladders. So to stop ladders from slipping, when you position a ladder, secure the top of the ladder, chock the bottom of the ladder, do whatever you can, get someone to hold the ladder, do whatever you can to stop the ladder from slipping.